Hey, evening, everybody. It's Tuesday evening, waiting for the Nuggets game to start. This is our exam 2. So question 1 deals with section 6.7, 6.7, and that is not on our final exam. Then let's see, moving on to integration. Okay, e to the t cubed. This is the same as e to the 3t dt. This is an exponential anti-differentiates to itself. And if the derivative of the inner function is a constant, you divide by the derivative of the inner function. There you go. Then x squared e to the x cubed. Some of you, I'll tell you, some of you did integration by parts here. You made u x squared. That would make du 2x dx. And then you made dv e to the x cubed dx. But then here's the problem. There's no antiderivative for that. So that doesn't work. Instead, do u sub, and let's switch colors. U sub, make u x cubed, then du is, or third du is x squared dx, and our integral turns into 1/3 e to the u du. And that antiderivative is 1/3 e to the u, and u is x cubed plus c. There we go. So let's take all of that, copy, paste. Why isn't that pasting? Let's try that again. No, okay, I think that did it. Let's see, we ended up with more than we wanted, but whatever, here we go. Okay. This one though takes integration by parts. So because of the 3x and the x cubed, this is not the same as the previous problem. So let's do u as x squared. Oh, and let me say LIPET. So x squared is a polynomial. E to the x squared is an exponent. E to the 3x is an exponential. So pick x squared to be u. Then du is 2x dx. Dv is e to the 3x dx. That makes v e to the 3x over 3. I'll tell you, a handful of you don't often include these dx's, and that's part of the process. You'll lose points for missing that. Okay, so there's our substitution work. Then we'd have u and v together. So that's x squared e to the 3x over 3, evaluated from 0 to 1. A lot of you didn't put bounds there, minus the integral 0 to 1 of v du. And that's going to be 2/3 x e to the 3x dx. Many of you did not put bounds there. Then we'd have x squared e to the 3x over 3 from 0 to 1 minus 2/3. And then we need integration by parts again on x e to the 3x. So round 2, this is round 1. Round 2. Let's see, round 1 happened on this piece. Round 2, there we go. You might hear my family in the background. We're at home just doing stuff. I don't know why the Nuggets game isn't starting, but you know, we're wanting to watch the Nuggets game. Round 2, u is x, du is 1 dx, dv is e to the 3x dx, v is e to the 3x over 3. So uv is x e to the 3x over 3 from 0 to 1 minus the integral from 0 to 1 v du, that's 1/3 e to the 3x dx. Okay, so now let's
not want anything with these goals or where.
Right out. Let's see. Okay, so we would have x e to the 3x over 3 minus in there, and now the antiderivative would be e to the 3x over 9. All of this from 0 to 1. So distributing the 2/3 gives us
That's shorts.
2/9 x e to the 3x plus 2e to the 3x over 27, all this from 0 to 1. You plug in a 1, and it's 1 e to the 3 over 3 minus 2/9 1 e to the 3 plus 2/27 e to the 3 minus what we get at evaluating at 0. It would be 0 minus 0 plus 2/27 e to the 0, which will be 2/27. Okay, so then we get e cubed over 3 minus 2/9 e cubed plus 2/27 e cubed plus, no minus 2/27. So these first several terms, these three are all e cubed terms, and you just need to find a common denominator there. So the common denominator is 27. So this needs to be scaled by 3. This needs to be scaled by 9. And that would give us something over 27 e cubed minus 2/27. And the something is 9 minus 6, that's 3, plus 2, that's 5. Okay, this is a trig integral. You have powers of cosine, powers of sine, and you have the presence of an odd power. And when you have a presence of an odd power, you take an even power, sine 2t cosine t dt. So we pulled off a single power from cosine cubed. That leaves us with an even power. And then the way forward is to switch cosine squared t into its Pythagorean identity involving sine squared, and making u sine. That'll knock out cosine t dt with a u sub.
Was what? It was 21. You don't want to.
Okay, so 6 cosine squared. So cosine squared is 1 minus sine squared t. All of this cosine t dt. So make u the sine of t. That will switch us into 6 times 1 minus u squared, and then we need to handle the cosine t dt, and that gets handled with du. Du, then right now our bounds are with u, or rather our bounds are with t. Our integrand is with u. So I'm going to switch the bounds. So if we switch the bounds. All right, so we have u pi halves.
Maybe we should put.
U pi halves is sine pi halves. That's 1. Sine 0, 0. So the bounds switch 0 to 1. We have 6 times u squared minus u to the 4. That's taking u squared and distributing it, and then du. So it's 6u cubed over 3 minus 6u to the 5 over 5 from 0 to 1. When we evaluate at 0, it's 0. So at 1 is 6 over 3 minus 6 over 5. What is that? That's 2 minus 1 and a fifth. I guess you could do a common denominator, but 2 minus 1 and 1/5 would be 2 minus 1 is 1, and then a fifth less than that is 4/5. I think we're at 4/5. 4/5, but you could check another way. You could find a common denominator,
Actually,
and that's a certain amount of 15ths. 30 15ths minus 18 15ths. And that is 30 minus 18. It's 12. That's 4/3, and then that's 5/3. So 4/5. There you go. Evaluate this integral. That's a trig sub. You know it's trig sub because of this 4 squared minus x squared. So make u 4 sine theta. That tells you a couple things. That tells you you have a triangle. Sine is x over 4, and that's some old horse. So x is opposite. 4 is adjacent, or a hypotenuse adjacent. 16 minus x squared. Then if you take the derivative, dx is going to be 4 cosine theta d theta. So you need to do all that substitution work for some points. Then replace your integral. The dx in the numerator is 4 cosine theta d theta. Denominator is 16 minus x squared. X squared would be 16 sine squared theta. And all of that to the 3 halves. Okay, so then keep the numerator. Simplify the denominator. That's the root for the half part of 16, 1 minus sine squared theta, and then all of that cubed for cosine theta d theta. If you take the root of, well, let's do that for 16. This 1 minus sine squared is cosine squared cubed. Our denominator, the root part, turns into 4 cosine theta cubed. So we're left with, we have 4 cosine thetas in the denominator, 1 in the numerator. So we have 2 of them in the denominator. It's 16 cosine squared theta d theta. Then that would turn into, let's see, the integral 16th secant squared theta.
I found them like on the same day. And I remember
That's the 16th. Tan theta plus a constant. Tan theta is opposite over adjacent. Opposite is this one, adjacent's that one. X over root 16 minus x squared plus c. There you go. Okay, partial fractions, because you know this is a polynomial. It's a rational function, and you can factor the polynomial. This is the same as 15 over, and if you factor that x, what, 4, 1 plus negative, that would give you minus 4 plus 3. Okay, so then this will split into an a over x minus 1, a b over x plus 4. If you find a and b, 15 is equal to a times x plus 4 plus b times x minus 1. When you let x be negative 4. When x is negative 4, then 15 equals, the a term goes away, and you get b times negative 5. This tells you that b is negative 3. When x is 1, that's 15 equals 5a. And a is 3. So our integral turns into 3 over x minus 1 plus negative 3 over x plus 4. Oh, we have dx in there. So natural log absolute x minus 1 minus 3. Natural log absolute x plus 4 plus c. That is a c. Proper integrals. Let's see. You're going to need a limit. And this one tells you it's improper. So that clues you into there's something wrong with the integral and you need to use a limit. You're going to get points for limit notation. For an improper integral, perhaps you have in your bounds like an infinity. That tells you it's improper. Here, the bounds are normal 0 to 2, but the issue is at 2, because if you plug a 2 in there, 2 minus 2, you get 0 in the denominator. That's not cool. So set up a limit. Use any letter you want. Typically, we're using n. And it approaches the problem value, in this case 2. And the interval is from 0 to 2. And so the values in the interval are less than 2. Like 0, a half, 1, 1.5, 2. I mean, you're approaching 2 from below 2. So it's 2 from the left or from below with values smaller than 2. And then we're integrating 0 to n. You replace the problem issue with n, 2 minus x dx. All right, then you keep your limit until the very end. From 0 to n. Okay, that antiderivative. I think a lot. Okay, so if you have a constant, doesn't matter if it's 1 or whatever, constant over something with the derivative being a constant, then your answer is natural log. And it's natural log of that denominator, but the derivative of the denominator is the constant -1. So you divide out by -1. This is no different than what we had before. This is e to the 3x divided by the constant derivative of the inner function. Here the inner function is 2 minus x. Its derivative is -1. We divide by that -1. What you can't do, 1 over 2 minus x, is not the same as a half minus 1 over x. It is not the same as this multiplied. So you can either remember how that natural log works or do a u sub. You could make u 2 minus x, du is negative x, or negative, so u is 2 minus x, du is negative dx, negative du is dx, and that negative is that negative right there. Okay, so negative natural log 2 minus n minus negative natural log 2 minus 0. All right, we're approaching 2 from the left. 2 from the left means we're approaching, this n is approaching 2. So let's do that. That n approaches 2. All of this then approaches 0. And it would approach, let's see, 0 from the right, which matters. Because, well, I guess it wouldn't matter because you're absolute value bars. If you approach 2 from the left, then pretend this n is like 1.98, then 2 minus 1.98, that's positive. We're approaching 0 from positive values. Either way, this, let's take that limit away. We're evaluating now. All right, then if we're approaching, we have negative natural log in the input is approaching 0 from the right, plus this natural log 2. If you approach 0 from the right with natural log, let's use green, this stuff goes to negative infinity. And then we have this negative on the outside. So that's plus infinite. We have infinite plus natural log 2. We should get infinity. That's telling us, what are the questions? Evaluate or state that it diverges. If it diverges, right, diverges. Okay, so it diverges. There you go. If this limit were a value, let's say this piece went to 0 and we ended up with natural log 2, then the integral would converge. It would be converges. And 2, natural log 2. That would be the area under that curve. All right, next question. Determine whether the following series converges or diverges. This 2 series, 1 to infinity, 8, a fifth to the k minus the sum, 2/5, 5, 6 to the k. So both of these are geometric, and the size of both ratios is less than 1. So both converge. And does it say, okay, determine whether, okay, to determine if they converge, so both are geoseries. In one, oh, there's the Nuggets game. In one case, the size of the ratio is a fifth, and that's less than 1. In the other case, the size of the ratio is 5/6, less than 1, both converge. Then, if you have a geometric series that converges, they both series converge. All right, so if you have geometric series that converge, they converge to some fractions. The denominators are always 1 minus the actual ratio, whether it's plus or minus. So a fifth and 5/6. If this had been negative 5/6, then this would be negative here, and we'd end up adding. But for convergence, we look at the size of the ratio, just the plus version. We don't care about the minus version. Then the numerators are the first terms of the series. So first term of this series is when you plug in k being 1, because that's the starting index. If you plug k1 there, then you get 8 times a fifth to the 1. That's 8 times a fifth. That's 8/5. The next one, plug in a 1 here. This will be 2/5 times 5/6. The 5s cancel. 2/6, that's a third. You end up with a third. Okay, so this already converges. What it converges to, we have 8/5 times the denominator is going to be 5/5 minus a fifth. That's 4/5 times, okay, 4/5 and then reciprocal 5/4. That's going to be 2 minus a third times the reciprocal of the denominator. The denominator is 6/6. That's 1/6. So 6/1 like this. 6/1. That's 2. Did we really get 0? You know what? I'm going to check the answer. I actually thought we changed that, but maybe we didn't. 0. There you go. Okay, let's keep going. Okay, this I think threw some people, but let's talk. So let's see. Okay, so in the case that you have a converging series, so let's say you have a series. starts at 1, and it's a sub k, then it's the terms a1, a2, a3, plus dot, dot, dot. And let's say it converges to, I'm going to use S for sum, S for sum. Then this series converges. And when you have a series that converges, you know a couple things. If it converges, it equals some value for its sum, and we're calling that S. When that happens, these terms of the series, the a sub k's, they have to get small. The a sub k's have to limit to 0 or converge to 0. You can write it like I'm writing here, AK goes to 0, converges to 0. You can write the limit of the AKs is equal to 0. The AKs get small. They have to. That's the only way that this series would converge. If they didn't get small, if they approached 1 or anything other than 0, then that series would diverge by the divergence test. Not only is the sum S, but you know that if we were to build a sequence of partial sums where we pretend you're right here and you're, here we go, let me move this, the AKs go to 0. Oh, let me put that back. Are you kidding? There we go. All right. So let's say you are right here and you're going to walk through the terms of the series. And as you do that, you're going to add them up. So as you walk through A1, you put A1 in your basket, and that's what your sum is right now. Your partial sum is the first term. And then you keep walking and you add up the first 2. Now you've added up 2 terms and you're getting closer to the actual sum. And then you keep walking and you add up 3 terms. Then you add up 4 terms. And as you add up these terms, and you keep walking term by term and you keep adding a term to your bucket, then you keep getting closer and closer to the actual sum of the series. And if you listed these terms, these sums, partial sums, here, let me write it down here, partial sums. So if we add up the first term, and then the first 2 and the first 3. So, and it says A sub n is the partial sequence of partials for this A sub k. So A sub n, that sequence, is A1, and then A1 plus A2, and A1 plus A2 plus A3, dot, dot, dot. And A1 is A1. A1 plus A2 is A2. A1 plus A2 is capital A3, so forth. So these are converging to the sum, just like the series is converging to the sum. So that's the situation. And so A sub n is the sequence of partials for A sub k's, B sub n sequence of partials for B sub k, and then answer the questions. Okay, so here you have some AKs, they go to 1. So these terms, you add them up, and each term eventually begins to look like 1. So you're adding 1 plus 1 plus 1 plus 1, and you get infinity. So this diverges. The limit of the series would go to infinity. Assume the sequence of partials is 20. The series would also go to 20. The sequence of partials and the series do the exact same thing. Up here, they either both converge to S or they both diverge to infinity. Next question. Okay, so here you have this being 20. This, the series of the first 3 terms of the series K, that's 1 plus 2 plus 3, that's 6. So 26 converges. Each of the following sequences, pay attention, these are sequences, not series. You're not going to use your series convergence sheet. So to decide if a sequence converges, you take a limit. The limit of this, it goes to 2. that converges. You know it goes to 2 because the powers of the numerator and denominator are the same. They're both polynomials. And so the limit is the ratio of leading coefficients. 4/2 is 2. The limit of the next one. You have a polynomial here. Let's see. Polynomial there, exponential there. You cannot compare powers, but you can compare growth factors. So e to the 2k as a exponential, it grows faster than 2k plus 3. So it gets to infinity faster. Like the numerator is going to infinity, so is the denominator, but this one wins. So it's like infinity over a number, and that's infinite. So we diverge as a sequence goes to infinity. If it had been the other way around, like 2k plus 3 over e to the 2k. In this case, infinite, infinite, but this one wins. It's like a number over something getting bigger, and that's 0. That would converge and go to 0. What are we at? Okay, so we have a series. Okay, determine the test. And okay, so for this exam too, we had 3 tests that we were considering: divergence test, geometric, and p-series. This does not fit p-series or geometric, so you're immediately into the divergence test. And then for the divergence test, you're taking the limit of the AKs, and the limit of the AKs is 2, just like, wasn't that the one before? Yeah, 2. Okay, so that's not 0. The terms don't get small, they approach 2. Again, you're eventually adding something plus something plus something plus something that's like 2 and 2 and 2 and 2, and that goes to infinity. It diverges. 2/√k, that's p-series. That's going to be the series of 1 to infinity, 2 over k to the half. So p-series, p is a half. It's less than 1. P equals a half. That's less than 1. Series diverges. This one, geometric. -4 to the k, -4 to the 1 over 3 to the k, and then let's write it as -4 times -4/3 to the k. All right, so this is geometric. The r is -4/3, but the size of r, the size is going to be -4/3. The size is a +4/3, and that's bigger than 1. So we're going to diverge. The negativeness doesn't matter with it being less than 1 to imply convergence. It's the size that matters. And then the only negativeness that matters is when you actually find the sum. If it were -3/4, well, then in the denominator, it would be first term of the series, 1 minus a -3/4. Then the sign matters. But here, sign doesn't matter. 4/3 is bigger than 1. We're going to diverge. Are we done? Hey, we're done. Check that out. All right. Y'all take care. And I might, yeah, y'all take care. Reach out if you need to. Okay.